Right, question 3, part A. The diagram below is an arrangement for analysing the light emitted by a source. Suggests a light source that would emit a continuous spectrum. A light source that would emit a continuous spectrum is any source of white light. So you could say a filament lamp or the sun, for instance. So any sensible source of white light would get you a mark for that question. Part B, the light source emits a range of wavelengths from 500 to 700 nanometers. The light is incident on a diffraction grating that has 10,000 lines per meter. Calculate the angle from the straight through direction at which the first order maximum for the 500 nanometer wavelength is formed. So using the diffraction grating equation, what we can see is that we've got our, we can firstly work out our diffraction grating size, which we've done there, and then we've got our wavelength for 500 nanometers. Rearrange the equation so we can get sine theta, and once we get that answer we need to inverse sine the answer to get the angle, and the angle we should get as 0.286 degrees, or 0.29 would probably be a more appropriate answer looking at the significant figures used in the question. Part 2, calculate the angular width of the first order spectrum. So in order to do this we need to remember this thing, that we're looking at two distinct edges, if you want. We've got the 500 nanometers through to 700 meters. So in order to get the width we need to find out the difference between those two. So in order to do that we've already worked out that for the 500 nanometers, same process for the 700 nanometers, and then to get the difference we need to take away the larger from the smaller, and therefore if we do that we'll get an answer of 0.114, etc, 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 which would round to 0.115 degrees. Part 3, what we're looking here in part 3 is that we can see that the detector is positioned 2 meters from the grating. So big D in this case is going to be our distance of 2 meters, capital D. Calculate the distance between the extreme ends of the first order. Well, we've got the angular difference, so what we're looking to find is Y. We're looking to find that width of the first order spectrum. So using either tan theta over yd or sine theta over yd that we looked at in the PowerPoint presentation, we can rearrange that and put in our figures that we've got, substitute in our values, and we should get a width of 4.0 times 10 to the minus 3 meters. Question C, the single slit is initially illuminated by light from a point source that is 0.02 meters from the slit. State and explain how the intensity of light incident on the single slit changes when the light source is moved from its position to a position of 0.05 meters from the slit. So what we're looking at here is we're looking at a distance that's increasing. So you should be familiar with the idea that as we move something away the intensity is going to decrease. Think about it as well if you think about if you're using a spray can, the closer you are, the more intense the spray, and the further away out the more diffuse it is. So if we look now at this question here, we can say, which we should know pretty straightforward, is that light intensity, the light intensity would lower, or sorry, not the light, yeah, the light intensity would lower because the energy spreads. Okay, so they're the two key points. But in order for you to access the full marks of this question, you need to show your understanding of the inverse law. So you should be familiar with the inverse square law. So as what happens is that the intensity is basically the inversely related to the inverse square of the distance in this case. So what we find is that in position 1 we would have an intensity of 2,500. Units here would probably be something like lux if we're looking at light intensity. Or position 2, what we're seeing is that that has dropped significantly because of the inverse square to 400 lux. So if we want to make something meaningful in our final statement here, we can mention the inverse square law, and that as a factor what we're going to see is that the intensity is going to fall by a factor of 6.25, okay, or the ratio is the light at position 2 is going to be 0.16 the intensity of the light in position 1. Either one of those statements would get you the third mark.